Hello and welcome to this new video on my DIY remote control project. This video and the next one will be a little bit different than what we used to see until now. What I will show is the way I have implemented what I consider the very last feature missing on the console before to start a testing production, which I plan to have at the end of this semester, which is the online firmware update procedure. Before to start, I would kindly ask you to subscribe to the channel, to give a thumbs up to the video if you liked it, and to hit the bell in order to stay tuned. So there is not much to say about the fact that a digital electronic device needs to have an online firmware update procedure. Resolution of bugs, in the first period this will be something that will happen extensively, I suppose. The addition of new features that you can develop via software, and so on and so forth. As a reminder, my system is composed by two groups of elements that implement an MCU. There is the first group, let's say, which is the main board. The main board is the big PCB that you have seen in the past video, the one with the tray bar, with the jog wheel, all the buttons, the USB connectivity to the DAW, and the UART connectivity to the channel. This board features an STM32A723, which for sure will require to have an online firmware update procedure. And then there are the channels, 8 channels plus the master. These implement an STM32F072, and also all this chip will require to have an update procedure. You will see that for the channels, the update procedure will be managed and controlled by the main board, where the main board itself and for the channel will also have the capability to connect online to download the software. In this video, we will concentrate on the main board part, and I will show you a demo in order to see the way it works. In the next video, we will see the way it works on the channel, which I think is quite interesting and nice to see. So there are 4 actors here involved in the way I have implemented this feature. The first one is the server. The server is where the new version of the firmware is residing and where the software is residing in order to implement the discovery of the new versions and then the download of the new version. In this case, it's a REST API web service that I have developed in .NET 8. Then there is, of course, the main board, what we have just discussed. There are the channels, and finally there is the end user. The end user is the one that needs to agree on activities and that is informed in case of error or successfully completed procedures. So let's start first of all from the discovery part of the new version. Here you are on Postman. Postman is an online application that allows you to query an online API, like in my case. In my system, I have developed basically 2 calls which are interesting. The firmware update one is the call dedicated to the discovery of the new version. So if I call it, as you can see, what I get is that there is a new version online available and that the version is 101 that has been developed in these dates and that has this size in byte. So let's get back to the schema. The main board make the request, get back the new version, compare the new version online with the one installed. If the version is the same, the end user is informed that there are no new version available. If the new version is available, then it goes on, requesting the agreement to download to the end user. If the end user give an OK, the main board can start the download activity. The download activity is done through this download firmware call. The download firmware call has in the get a parameter which is called a chunk number. And at this point I need to explain one simple thing. Or 2 things actually, to be precise. The first one is that you cannot transfer a stream of bytes through HTTP. If you want to transfer data through HTTP, you have to encode, to transform, to encode this stream of bytes in something that the HTTP can manage, like a stream of characters. For this reason, the software before the download is encoded in base 64. You will see in a moment what that means in a visual way. The second thing that I need to explain you is that the chip that I use to connect my system to the internet is a WIZnet 5500, which is an Ethernet chip driver that cannot download per session, in one session, more than 1460 bytes, so basically a little bit more than a kilobyte. You have seen before from this call that the size of the firmware is much more than 1 kilobyte. So there is the need on the server side to split the software in several chunks, and there is the need on the mainboard side to download every chunk in order to get finally the software available. That's the reason why you have the chunk number parameter. As from the first call, as you can see here, the mainboard will request chunk number 0. Chunk number 0, in fact, you don't get the software, but you get important data. You get the size in encoded form, so base 64. You get again the size of decoded, but most importantly, you have the number of parts, which in this case is 65. So the console knows that we'll have to iterate 65 times in order to get back the software. Once this activity is done, the mainboard starts requiring the first chunk, and then all the others until 65. If we put here 1 to download the first one, as you can see, again, we have the same data we saw before, but now we have the current part number, which is 1. We have the size of the first chunk in bytes and in the encoded base 64 way, which is 1 kilobyte. You have the size of the decoded version, which is 76.8, and you have another important value here, which is the CRC32 value. CRC32 is an algorithm to hash a stream of data. But what is hashing? What that means? It means that through an algorithm you can represent in a hashed way and reduced way, but unique way, a stream of data. I put available this hashing value in the server. The console downloads these elements. Then when it finishes to download the software, it performs locally a CRC32 hashing activity, and of course hoping to having the same value. If the value is the same, it means that the software that has been downloaded is consistent with the one that you have online. If the number is different, it means that something went wrong and the data either are not being downloaded completely or in some way came corrupted. So it's a consistency check, if you like. And finally, you have the content itself. These are the stream of bytes of the firmware for the first chunk, encoded in base 64, and in fact, as you can see, it's just pure text, ASCII text to be precise. And this, of course, can be transferred via HTTP. So getting back to the schema, the main board here will will loop from 1 to 65 to download every chunk, checking the CRC value. In case of error, will inform the user that something went wrong, and in case everything is fine, it will continue exactly until the end. When it will have completed the download, the system will have to save it in the memory of the MCU, ready to be installed. But it's not just the saving, because the mainboard, as we said, will have downloaded chunks. So first of all, the mainboard will have to reassemble the chunks into one unique stream, and secondly, we'll have to decode from base 64 to the byte stream as it was originally in the server. At the end of these activities, it will save. If all these activities goes fine, then the mainboard will be ready to install the new version of the software. Otherwise, it will inform the user that something went wrong. So here I'm going to demo all the activity that I have just depicted, with just one information more that I will show you at the end, which is how the installation of the new version of the firmware happened, which is not panel. What you can see here is an F4 Nucleo board, which I will use for the demo. I don't have yet the capability to connect the WizNet 5500 to my board, so I show you the demo here, but it will work exactly the same into the board. This is the 5500, which, as you can see, is connected via Ethernet to my router. Okay. First of all, we restart the board, and you can see that we have already some information happening on the screen. The first information that you see here is that the board, when the board is reset, it starts from an application which is called bootloader. This bootloader is a custom bootloader that I have developed. It resides in the memory just before the main application, and it has just two duties. The first one is to check if the flag is the update flag, which is a byte in the memory, is 0, in which case it jumps literally to the main application and it launches the main application. In this case, in fact, the flag was 0. It jumps to the main application. As you can see, the version of the main application is 100. The main application initialize the WizNet chip, connect to the Wi-Fi to the network of my LAN, get an IP from my LAN, and then make an activity which is called a DNS lookup. So on the basis of an internet address, that is this one, it calls the DNS server, and it requires to discover what is the IP that stands behind this address, in which case is this one, and this is the IP of my server. At this point, everything is set in order to make all the activities that we have saw before. I click the button, and then the procedure starts. Let the procedure complete. I will pause for a moment because it takes some seconds, and then we will review what's happened. So the procedure has been completed. Let's review from the start and analyze what's happened, and if we are consistent with the draw that I've shown you. So we were here. The address of my API was translated into an IP by the DNS. As first thing, the system, the main board, has checked, has connected to the server, sent a request to check. It's the firmware update call that you've seen before, and it discovered that in fact online there is a 101 version available. It says the version that is installed currently is the 100, so a newer version of the firmware is available, and it starts the procedure to download the newer version. As we saw before, it starts from the first chunk, which is this one. It knows that there are 65 chunks to download. It gets the software, it checks the CRC. As you can see, the CRC calculated locally and the one provided by remote, it's the same. So it means that the software that came down worked properly. And so it moves on to chunk number 2, doing the same, and so on and so forth until the end. We go to the end. The download procedure is completed. The number of bytes downloaded is this one, which match what was declared at the beginning. It starts the procedure of decode the data, so it has already assembled everything, and it have now to decode from base64 to the binary format. It complete, and in fact we got the same size that we got at the beginning, and so it goes saving into the backup area and setting the update flag to 1, which is the one that will be checked by the bootloader when the system will start. The new firmware has been saved in the backup area and it's ready to update to the new version. It requires the user to restart the system. Let's restart and see what's happened. And there you go. So what's happened is that at the restart, the system restarted from the bootloader. It always restarts from the bootloader application because it's the first one in the memory. The bootloader sees that the update flag is 1, in which case knows that there is a new version of the framework to be installed. It does this. It updates the update flag to 0 once again in order to because the installation of the new version has been completed, and it reboots automatically again the machine. It reboots the machine, it restarts once again from the bootloader. The flag is 0, it was set 0 here, so the system jumps to the main application, which at this point should have the new version of the firmware, which is in fact the case. As you can see, currently installed version is 101, where the original one was 100. So the procedure went fine. I got the new version installed. The Ethernet controller, the WizNet 5500 is reinitialized, and the procedures start again, being ready to make a new check. Of course, if I launch again the check of the new version, it will do again the call firmware update that we saw before. It will get that online there is version 1.1, which happens to be the same that is installed already, and so it will inform the user that he or she have already the last version installed on the machine. This completes the procedure. The system connect to the internet, download the software, pack the software, and install the new software in a completely autonomous way. So the main board, the feature on the main board, is completed and working. In the next video, you will see the way it works for the updates on all the channels. For now, thank you very much for your attention. I hope that this video will give some light on how this firmware update procedure works, and maybe give some help to someone if he's developing the same thing. Thank you very much, and see you in the next video.